Have you ever pondered how a balance can tilt with unequal weights? And why this simple concept carries such importance in our world? Today, we're about to embark on a journey that explores this fascinating concept, drawing from physics, mathematics, and even biology. Imagine a balance, a simple device with a fulcrum at the center. This balance can be in a state of equilibrium when the system comes to rest. But what happens when we disrupt this equilibrium? There are two main methods to tilt a balance: adding unequal weights to each side or shifting some weight from one side to the other. Consider the first method. Suppose we have a balance with equal weights on both sides. Now add additional but unequal weights to both sides, as shown by adding the weights S1 and S2 in left side of the picture. The balance tilts towards the heavier side. The degree of tilt depends on the relative difference in the weights. This is a straightforward example of how adding unequal weights can disrupt equilibrium. The second method is a bit more subtle. Instead of adding weight, we shift some amount of weight from one side to the other. This is labeled as delta W in the right side of the picture. Even though the total weight remains the same, the balance tilts. This tilt occurs because the distribution of weight has changed, creating a new center of mass. In both cases, the balance tilts because the forces on both sides of the fulcrum become unequal. Tilting a balance involves either adding unequal weights to each side or moving some weight from one side to the other. Mathematically, this can be modeled by an equation that accounts for the transfer of weight between sides. This is the delta W in the pictures. This is done by equating the two ratios. We inherently expect that the ratios of weights for the two examples are equal to produce the same in tilt of the balance. This can easily be proven to be true, but isn't shown here. These two equivalent ways to tilt the balance can be equated and solved for delta W, as shown in the picture. The remarkable thing about this equation for delta W is that it obeys a well-known physiological law called the Weber-Fechner law, which has been experimentally measured and deduced for all our senses. This was first described for a simple balance in the following publication: Weber's law, modeled by the mathematical description of a beam balance. Mathematical Biosciences 122, 89, 94, 1994. This is a remarkable and surprising observation from such a relatively simple equation derived for the tilt in a simple balance. Now, how does this tie into Weber's law? Well, Weber's law states that the difference threshold, or the minimum difference in stimuli required to perceive a change, is a constant proportion of the original stimulus. In the context of our balance, this means that the noticeable difference in weight, which is the delta W term, is proportionate to the total original weight. This law is fundamental in sensory perception, explaining why small weight differences are more noticeable on a light balance than a heavy one. These principles aren't just confined to balances and weights. They permeate every aspect of our lives, from the way we perceive the world around us to the functioning of our cells. In biochemistry, for instance, receptors function much like a chemical balance. They respond to different concentrations of molecules, maintaining our homeostatic equilibrium that is crucial for our health. In conclusion, the concept of tilting a balance with unequal weights is a powerful one. It illustrates the delicate balance of forces in our world, underpins the Weber-Fechner law, and echoes the importance of equilibrium in life and scientific research. Whether we're adding different weights or shifting some from one side to the other, we're continuously interacting with balances, tilts, and equilibrium. It's a dance of forces, a ballet of balance, which creates a symphony of all the net shifts of the receptors occurring within our bodies, and a testament to the intricate interconnectedness of our universe.